Hi everyone, and welcome to another LIC class. So before the exam, by the way, we had a review session, and because of the exam, we didn't have any class last week. And on Thursday, I had to attend a conference, so we didn't have a class on Thursday, and on Tuesday we had the exam. Before in the last class, I could say, we went through practical limitations of op-amps. Specifically, we spoke about the lower cutoff frequency of the op-amp. And we realized that a lower cutoff frequency of the op-amp, an op-amp itself, the frequency could go down to 0 hertz or DC. So the element that determines the lower cutoff frequency of the op-amp is actually the coupling capacitor, which is connected to the op-amp. So the op-amp itself, on its own, it doesn't have a lower limit on its cutoff frequency, but when we add a coupling capacitor, it creates an RC filter, low pass filter, and therefore it puts some limitation on the op-amp. And the way that we calculate this lower cutoff frequency is using this equation, same as a passive low pass filter. FC is going to be 1 over 2 pi RC. R is the resistor connected to the ground here, and C is the coupling capacitor. We also learned about another limitation that these op-amps have is the speed of switching, or what we call the slew rate, or the speed of response. For a 741, that's around half volts per microseconds, meaning in 2 microseconds, the voltage could change up to 1 volt. We also have faster op-amps like the LF411, which is 30 times faster than the LM741. So what effect does this slew rate have on this on these op-amps? The problem that occurs when we have a small slew rate is that when you have a very fast changing input, in other words, we have a very high frequency input, the output and the op-amp could not keep up with that input. So for example, here, if this is our ideal output that we are looking for, and we have an input that looks like this, it's a square signal, and it goes from 0 to 2 volts down to 0. We would like to have an ideal output at the same time. Maybe give it some gain. Here the gain is 1. But imagine if I have a signal which looks like this, and the input is 20 millivolts. So 100 times gain of 100, it gives us the output. And we want that ideal output to look exactly like an input for a couple of reasons. First reason, obviously, if we have information, this signal, we don't want to have any distortion. We don't want the shape of the signal to change. So if we have an audio signal, obviously, if you change that shape, and instead of a square, you have a triangle, a rectangle, you have a triangle signal, it's going to completely destroy the information. So what happens if we don't have a fast op-amp? So if we have an op-amp that has a slew rate, which is pretty low, the response time takes a while. So for a 741, for example, the slew rate is pretty low, meaning the output would not immediately change. It takes some time for the output to follow the input. And when it reaches its maximum, the input has already changed. So this should change as well. So what we're going to have is, instead of having this ideal rectangle or square output, we have a triangle output. The reason is that 2 reasons, mainly. 1, the op-amp is not fast enough, and number 2 is the output voltage, the maximum voltage is so high that that op amp could not reach that output. So if the output voltage was around, let's say here, I'm going to draw another one with the black one. If it was down here, the 741 could do it with the blue color, could reach this, and you're going to have a better signal compared to that. So if I had, instead of 2 volts, I had 0.2 volts, for example, we won't have that much of a problem, okay? Because it's going to still reach that. When we increase the output voltage, the maximum voltage, and we have a slower op amp, those combination creates an undesirable situation, which we would have a distorted output signal. So what is the solution? 2 ways that we can address this problem. Number 1 is to lower the maximum voltage that we want, which in most cases, it's not an ideal solution. We want to have a certain gain. It's like you have an audio amplifier and you have to reduce the volume. So what is the purpose of that amplifier if you can't increase the volume above a certain level? So you're going to eliminate the advantage of having an amplifier in the first place. The better alternative is to use a faster op amp with a higher slew rate. So here we have replaced the 741 with a 411, which has a larger slew rate. And you can see that for that, it took like 6 microseconds to reach its peak, and immediately since the input changed, the output should go back. But for the 411, as we know from this table, the voltage, the slew rate is 15 volts per microsecond. So it's going to change much faster. You're going to have a better shape signal. Still, it's not going to be ideal like the one that you see on top, but it's going to be pretty close to that. You would never have an ideal slew rate of that one, and the ideal output would have a slew rate of infinite, which in real world we don't have. So is this part clear? Yes. So slew rate creates, if you have a small slew rate, creates a problem if you have a high frequency input. Most cases, when you have an audio amplifier, which the frequency is around 20 kilohertz, it's not a big deal. We already know from the previous slides, the previous chapters that we went through, is that the 741 has a gain bandwidth product of around 1 megahertz and a slew rate, which is 0.5 volts per microsecond. So 1 megahertz, anything, and if we give it a feedback, that's going to reduce it maybe to 200 kilohertz. The audio signal is usually around 20 hertz to 20 kilohertz. So it's in the range that the 741 op amp is going to perfectly function. But if you want to send radio communication, if you have a communication system between 2 devices, like a cell phone communication or a radio frequency, those are higher frequencies, and you can't use the 741. It's going to create distortion. It's going to destroy your signal. So the next chapter we're going to have is, so far we learned about upper cutoff frequency and the lower cutoff frequency of the op amp. We learned that the upper cutoff frequency of an op amp, it's determined by the characteristics of the op amp itself. And the lower cutoff frequency of an op amp is determined by the coupling capacitor and the filter that is connected to that. Now, how can we use that in our advantage? You may think the upper and lower cutoff frequency is a disadvantage or cons of an op amp, but actually we use those characteristics most of the time in our advantage and as a pro to create a filter, which we call low pass filter or high pass filter. So we have 2 types of filters. We have passive filters and we have active filters. So what are passive filters? Passive filters are made out of passive elements. We learned in the first chapter, in the first class, Do you remember what the passive elements were? So anything that doesn't create energy, doesn't produce energy, is a passive element, like a resistor, a capacitor, inductor, because they don't create any amplifying effect. They don't have any, they don't produce any power. Those are passive elements. So these elements don't have any signal gains, and the output is always less than the input. This is very important. The output level is always less than the input. And we have the active filters. So an active filter is made out of active elements. These active elements create a gain. They usually have an external power source, which they draw the power from that external power source. And some active elements components are, for example, are transistors, op amps, BJT, JFET, FET transistors, and so on. And filters are also named according to the frequency range of the signal that they allow to pass through them, while blocking or attenuating the rest. The most commonly used filter designs are low pass filter, high pass filter, and band pass filter. And notch pass filter is basically a band pass filter, and I'll explain, or what they call a stop band filter. So what is a low pass filter? The low pass filter only allows low frequencies to pass. So anything from 0 hertz to an upper cutoff frequency is called a low pass filter. And it looks like this. So it allows all the lower frequencies to pass. So this part is going to be the pass band, and anything else is going to be the stop band. So anything above a certain frequency is going to be blocked. High pass filter is the opposite of a low pass filter. It blocks lower frequencies and allows higher frequencies to pass. Again, we have the stop band and we have the pass band. So any frequency lower than its cutoff frequency would be blocked, and it's going to pass technically, in theory, up to infinite frequencies. And then we have a band pass filter. So a band pass filter is a combination of a low pass filter and a high pass filter. So if we combine a low pass filter and a high pass filter, we create a band pass filter, which looks like this. So blocks frequencies, which are, I'm going to say stop band, and pass band. So passes a certain frequency and stops the frequency, which are the lower from the lower cutoff frequency and higher than the upper cutoff frequency. So only the frequency between 2 points, the lower cutoff frequency and the upper cutoff frequency, are passed, and everything else is blocked. So what about, now what is the difference between an active and a passive filter? So both of them, again, low pass filter, high pass filter, band pass filter, the function is the same, but there are some difference between them. So one main disadvantage of a passive filter is that the output signal is always less than the input signal. So the gain is never greater than 1. The output signal attenuation is severe in multi-stage passive filters. The reason is that because we don't have any amplifying element in the system, after each stage, if we put multi-stages of filters, like if we add a low pass filter and a high pass filter to create a band pass filter, these two filters have at least one resistor. And each time that this signal is passing this resistor, the voltage is going to drop, the amplitude is going to drop. So you're going to create more distortion, more attenuation in the signal as well, because we don't have anything to compensate for the loss of the power in that multi-stage filters. And the best way to control the loss is through amplification of using through using a active filters. Filters can also be used to alter the frequency response and creating a selective output response. And we can create a narrow pass band system, which is selective, by the way, and we can pick certain frequencies. It's like hand picking those frequencies. So and we can make them wider, we can make them narrower. And the reason that this is very useful is, imagine that you have a bunch of frequencies. You have different radio frequencies. For example, one is 12 kilohertz, one is 20, one is 30 different stations. And imagine that my filter is this blue filter. What I can do is I can easily move this filter to pick up different radio stations. So if this is 12 kilohertz, this is 1 megahertz, this is 3 megahertz, I can just move them and what we call a frequency hopping and select those. This is one application. The other application is to just get rid of noise. So imagine that you have a walkie-talkie, and sometimes the walkie-talkies are in a what we call public domain frequency. You have a lot of noise. What we do is actually, when you see that the connection is not very good, you hear a lot of noise, white noise. The first thing that they would do is usually they would change the frequency. You'll go on another channel, what they call it. So changing those channels is technically you're shifting your filter, and you're moving the transmitter is sending a different receiver signal, and the receiver is just shifting that filter to get another frequency, which is on a channel or a line that is actually doesn't have noise on it. So reducing noise and having a selected frequency. There are a lot of so this is this is an example in a normal commercial daily use. When it gets into, for example, radars for airplanes or communication systems, if you want to have a secure communication system, it gets much more complicated. Imagine you want to have a very secure communication. Sometimes the frequency changes 100,000 times a minute or 1,000 times a second, something like that. It's crazy fast. They just switch channels very quickly. So if someone is able to pick, it's going to pick just a small portion of your communication. So we have that frequency hopping. One example, again, another example is in these radar systems. If something wants to avoid radar, they just switch frequencies and so on. So an active filter generally uses a op amp. The op amp has high input impedance, low output impedance, and usually an adjustable voltage gain, which is determined by the feedback resistor. One difference that is between active filters and a passive filter is a passive filter or a high pass filter. Well, in theory, we don't have upper cutoff frequency in a high pass filter for a passive filter. But for active filter, we have a cutoff frequency and the upper cutoff frequency. So imagine that you built a op amp which looks like this. And we already know that this is a low pass filter. I'm sorry, the high pass filter, because we have lower cutoff frequency determined by this capacitor and this resistor. So in theory, what happens is you're gonna have a lower cutoff frequency, which is determined by this FC, which is equal to 2 pi F C. But in reality, what happens is that we already know that op amp has an upper cutoff frequency limitation, which is determined by its gain bandwidth product. Okay, do you remember what was the upper cutoff frequency of an op amp or F2? It was the gain bandwidth over A noise. Yes. So in reality, an op amp has a limited upper cutoff frequency. And that cutoff frequency is determined by its A noise, which is the gain, and especially the gain bandwidth product, which is the op amp itself. Yes, please.
That resistor parallel to the input, what does that do for the filter?
Okay, that's an RC filter. That's a great question. Without that, we don't have adequate impedance to create that. If you want, I can dedicate another class for that. With basically what that does is grounding of the system. And in a filter, we usually have R and C together to create that impedance for the lower cutoff frequency. It's a part of the R. It's not a part of the circuit at all. That's just a part of the RC filter, and you need that impedance to be able to ground the voltage that is coming from the other side to the capacitor. That's a great question, by the way. But did you have RC filters? Didn't you have RC filters in signals and systems or circuits too? So that is a part of circuits. That's the reason I just touched base on that. But passive filters is a part of that. But that is a part of the impedance that is needed for the RC system. Without that, so imagine that R is 0, you know, it's going to create a problem, or it's infinite. You're not going to have a good cutoff frequency. Does that answer your question? Yes. So technically, an op amp doesn't have an infinite upper cutoff frequency. So when you build an active high pass filter, it's technically a band pass filter, because we always have a upper cutoff frequency, which is F2, which is determined by the gain bandwidth over A noise. So technically, we don't have a thing called a active high pass filter, I could say, because all active filters have upper cutoff frequency limit, which makes it a band pass filter. That said, we usually choose the upper cutoff frequency to become so high that doesn't affect with our circuit. So this could be around, let's say, 2 gigahertz, sometimes even. And the maximum upper cutoff frequency that we have, a high frequency that we want, we just want to filter out anything below, let's say, 20 kilohertz. Okay. And we're never gonna reach this frequency. So it's so far that we're not gonna even care about it. But in reality, this is the case for an op amp. So still, active filters are generally much easier to design than passive filters that they produce good performance characteristics, very good accuracy with a steep roll off, and low noise when used with a good circuit design. So the first filter we have is called the active low pass filter. Again, an active low pass filter is a passive low pass filter, and this part is a passive low pass filter, which looks like this, just connected to an active element. So you can, instead of that op amp, you could just put a FET amplifier. When you connect a passive low pass filter, and the left part is a passive low pass filter connected to an active element, and now you have created an active low pass filter. So the most common and easily understood active filter is the active low pass filter. its principles, our operations, and frequency response is exactly the same as those for previously seen of the passive filters. The only difference is that it uses an op amp for amplification and gain control. So for example, this one is connected. You can see that the input is connected to non-inverting input. And this, can you tell me what type of amplifier is this amplifier? Yes, it's a buffer. The negative input, the inverting, is directly connected to the output. So it's a unity, or what we call a buffer amplifier. Gain of 1. So this is I can say, the simplest low pass filter. It doesn't have any gain. The gain is 1. But it's an active filter. So this first order low pass active filter consists simply of a passive RC filter stage. So again, this is the passive RC stage, and we have the active element, which is the op amp. And as you know, it's a voltage follower, so the gain AV is equal to +1. So the advantage of this configuration is that the op amp's high impedance prevents excessive loading on the filter's output, while its low output impedance prevents the filter's cutoff frequency point from being affected by changes in the impedance of the load. While this configuration provides good stability to the filter, its main disadvantage is that it has no voltage gain above 1. However, although the voltage gain is unity, the power gain is very high, as its output impedance is much lower than its input impedance. If a voltage gain greater than 1 is required, we can use the following circuit. So, and this is in general. You may think, why do we even use a buffer? And we use the buffers in a lot of, especially in digital circuits. The main reason that we use a buffer is usually to separate the input impedance from the output impedance and create a buffer zone between them. Because, for example, in this case, if my output is, let's say, a speaker, that speaker has a very low resistor, and that low resistor now would be in parallel with that capacitor, and now it's going to compromise the filter itself. And the other thing is that resistor also changes as well. Okay, when it gets hot, you may have multiple stages of resistors, your potentiometer, and when you change those resistors, the cutoff frequency FC and this R changes. And now suddenly you're just shifting your filter all around the place. And we don't want that. We want this to be fixed at a certain frequency. That's the reason we use the op amp as a buffer, to be able to completely separate that, separate between the output and the input. Again, 2 main reasons. Number 1, we don't want that to affect the, and we want that to protect, actually. Sometimes if you have a very slow resistor in the output, what you're gonna do is you're gonna blow up your capacitor. It's gonna damage your system. So protection, and also having more stable system. So if you need a gain more than 1, we can use this. Can you tell me what type of amplifier is this? Since the input is connected to the non-inverting input, this is a non-inverting amplifier. For a non-inverting amplifier, the gain is 1 plus R2 over R1. So the frequency response is going to be the same as a passive RC filter, but this time we're going to have a gain. And the gain for this system, since it's a non-inverting amplifier is going to be 1 plus R2 over R1. Again, imagine we have two separate circuits. The first one is a passive LPF or low pass filter. And the second part is just an active element, which is an op amp. So combining these two will create an active low pass filter. So the right part is completely, you could just separate them and replace it with anything else. And on the right part, you see the amplification, the op amp gain, because it's a non-inverting, it's going to be 1 plus R2 over R1. Now, what happens in the low pass filter? So low pass filter, what happens if I give this a DC signal? If I give this a DC signal, DC is going to pass R3, just have a little bit of drop in voltage. So instead of this, you're going to have a little bit of drop in the voltage. It's going to be like this. Now this DC is going to charge the capacitor, yes? When the capacitor is fully charged, what happens to it? It becomes an open circuit. Again, the same analogy that I showed you. A capacitor, when you have a DC, it's going to be blocked because it's going to fully charge it and then it's going to. So now you imagine we don't have even that capacitor because it's going to get charged in the first few milliseconds or microseconds, depending on how big the capacitor is. So then all the DC would pass and it would get into the op amp and it's going to pass through the op amp. It's going to be amplified. And this is going to continue in low frequencies as well. Because again, for lower frequencies, the impedance of the capacitor is going to be so high again that this is going to act like an open circuit. But if we have a large enough frequency, a high frequency, at one point when it's going to overcome the impedance of the capacitor, that high frequency is going to pass this capacitor, yes? It's going to jump through the capacitor. And now what happens to the capacitor? The capacitor becomes a short circuit. So now the input has been shorted. In other words, this part voltage, I'm going to put A and B are going to have the same voltage, which is equal to the ground voltage, which is equal to 0. Now, because I've grounded the input, you're going to have no output. Okay. Now, how do we determine that frequency? Again, high pass filter, again, 1 over 2 pi RC. And the way that we determine the gain, since it's a non-inverting amplifier, if it was an inverting amplifier, the gain would be negative R2 over R1. Since this is a non-inverting amplifier, if you switch it, you're going to create an inverting amplifier. But the voltage gain, V out, Vn, is now it's not equal to an op amp. It's also depending on the frequency as well. So, let's analyze this equation. They're going to be determined by this equation. In this equation, AF is the passband gain of the filter. In other words, it's the gain of the amplifier, which is 1 plus R2 over R1. F is the frequency of the input signal in hertz, and FC is the cutoff frequency in hertz. So what happens is when the frequency, the input frequency is very low, in other words, F is less than FC. When F is less than FC, this is going to be a very, very small number. So imagine if F is 1 and FC is 10. Then F over FC in the power 2 is going to be 1 over 100. So now you're gonna have 1 plus 1 over 100 square root of that, which this is gonna be very, very close to 1. You agree? Therefore, V out, or let's say gain, AB, is gonna be AF over 1, which is gonna be equal almost to AF. So when the frequency is pretty low, the gain is determined by the gain of the op amp, okay? At the cutoff frequency, when F is equal to FC, V out, again, imagine F is 100 and FC is 100. So you're gonna have 100 over 100 is gonna be 1. 1 plus 1 is gonna be square root of 2. And AF over square root of 2 gives us exactly the 3 dB or the cutoff frequency, which is equal to AF over square root of 2 or 1.44, square root of 2 or 1.44, which gives us 0.707 of AF. So you're gonna have this going on, and exactly at FC, the gain is gonna be 0.707 of the maximum. And this is the maximum gain in the band pass. And anything above that, you're gonna see a decrease in the gain. Now, let's solve a practice problem. So imagine our input frequency is 10 kilohertz. The cutoff frequency FC is 20 kilohertz. R1 is equal to 10K. R2 is equal to 20K. Vn is equal to 2 millivolts. What is V outcome? Again, the gain is going to be equal to AF over square root of 1 plus F over FC in the power of 2. Okay, now I want you to find second part. I want to find V out. Oh, I don't think I have time for that one, but yeah, I don't have time for that one. For the second part, we're gonna solve it another day. So AV is equal to V out. What was your answer, by the way? 0.37, okay. So AF, as we know, is gonna be 1 plus R2 over R1, which is gonna be 3. 1 plus 20 over 10. So V out over V in would be 3 over square root of 1 plus F, which is 10K, over FC, which is 20K, and a power of 2. So it's going to be 1/4. 1 plus 1/4 square root is going to be, what is going to be? 1.14, and 3 divided by 1/4.
1.118.
Okay, and 3 divided by that. What is the final answer for this? What did you get? 2.68. Yes, for this. Yes. This is going to be equal to V out over V in. Therefore, V out would be equal to 2 times 2.68, which is going to give you 5.37. You all have the same millivolts. Okay, I think we're out of time. This is it for today. In the next class, we want to continue this and start with the high pass filter. Thank you so much. I would see you on Thursday.